Hello guys, this is Rick from MathX, and today we'll be doing the number 21 from the AMC 10B of 2021. Now, this problem is actually surprisingly easy for a number 21, because even though it looks a little bit tricky with the confusing diagram, it is actually a pretty standard geometry problems, and we're going to only be using simple geometry concepts like similarity and Pythagorean theorem. So without further ado, let's just get into the problem. A square piece of paper has a side length of 1 and vertices A, B, C, D in that order. As shown in the figure, the paper is folded such that vertex C meets edge AD on point C', and edge BC intersects edge AB at point E. Suppose that C'D is 1/3. What is the perimeter of triangle AEC? So the problem is quite simple. We have a square piece of paper. We fold this piece of paper such that the vertex C is mapped onto C'. And from there we know that C'D is 1/3, and we want to compute what the perimeter of triangle AEC' is. So just like any other geometry problem, the first step would be to make your own diagram. So I'm going to take a copy of this, and I'll just make a copy to the side and edit directly on top of that copy. So here's my enlarged copy of the diagram. With this diagram, I'll edit on top of this, labeling known side lengths and known angles, along with any additional points that I might need to label. So first, it tells us that C'D is 1/3, so I'm going to label that length here. Then, since it tells us that this is a square piece of paper with side length of 1, we can actually directly compute AC', since we know that AD, one of the side lengths of the square with side length of 1, is 1. So, thus AD is 1, C'D is 1/3, AC' is 2/3. Now from here, there's not really any other lengths that we can directly label, since most of the other shape has been warped. However, we can start identifying some angles. First, we can say that angle EAC' is a right angle. And we can say that because it is part of the original square piece of paper. It is an angle in that original square piece of paper. And we know that the angles in a square are all right angles. So thus, angle EAC' is a right angle or 90 degrees. Similarly, C'D and this point of intersection, which I'll label as I, is also a right angle. And it is a right angle for the same reason that angle EAC' is. This is because it is part of the original square, and its angle was not altered when the folding was happening. Finally, we can say that angle EC'I is also a right angle, because this angle wasn't changed whatsoever. It was just folded about this intersection point I, and it was mapped to C'. This angle itself wasn't changed. So this angle EC'I is a right angle as well. Furthermore, we can also figure out that some angles are complementary to one another. For instance, we can understand that angles AC'(E) is complementary to angles IC'(D). And we can say this because we know that since ACD is a straight line, it must have an angle sum of 180 degrees. Since 90 degrees is already being used up in the angle EC'I, that means the other two angles, AC'(E) and IC'(D) must add up to 90 degrees as well. Similarly, we can also say that angle AEC' is complementary to AC'(E). And this is because since these are all angles of a triangle, they need to add up to 180 degrees. So we can say, so since angle EAC prime is already 90 degrees, the remaining two angles, AEC prime and AC prime E, have to add up to 90 degrees as well, meaning that these two angles are complementary as well. Now, remember, the complements of the same angle are congruent, so that actually lets us say that angle AEC prime is the same as angle IC prime D. Finally, we can figure out that angle C prime ID is also complementary to angle IC prime D. And this is because, once again, these are the angles of a triangle, so they have to add up to 180. We already have 90 degrees being used up in angle C prime DI. So we know that the other two angles in that triangle, DC prime I and C prime ID, have to add up to 90 degrees as well, meaning that they're complementary as well. Using the same logic, complements of the same angle are congruent. We can see that angle C prime ID is congruent to angle AC prime E. So right now we have two triangles. Triangles A, E, C prime, and triangles D, C prime, I. And we see that they have all three angles in common. So since all three angles are the same in these two triangles, we can easily say that these two triangles are similar to one another. So we can actually create some variables and set up a ratio. Due to their similarity with one another, we can say that x by 2/3, where x is the side length of AE, is equal to 1/3 by y, where y is the length of DI. And we just got this relationship due to the similarity, which we proved by just looking at their angles. Now the problem with this is we have two variables, and we only have one relationship, which means that in order to solve this, we need to get at least one more relationship using these two variables, or just one of these two variables. So we can do that by actually just thinking about what's happening when this is folded, C prime and I. Like, we can think about this length, C prime I. When the paper original ABCD was folded about this point I, this length, C prime I, did not change. This length, C prime I, is actually the same as the original length, CI. And this makes sense, because that was simply like a reflection about a line. And reflections will conserve the length between the 2 points being reflected. So we can say that C prime I is equal to IC, which is also quite interesting, because we can compute for C prime I using Pythagorean theorem. We can get that C prime I is equal to the square root of y squared plus 1/3 squared, which is 1/9. So just using that logic, we can compute that C prime I is just this value. And since C prime I is the same as Ci, we can see that this value, the root y squared plus 1/9 plus y, has to equal to the original side length of the square, which is 1. So now we have another relationship. Since this is one equation and we only have one variable, we can actually use this to solve for y by just simply rearranging the equation. So we just keep the y squared plus 1/9 on the left hand side. We take over the y on the right hand side and just subtract it due to it just crossing the equal sign. And then we can square both sides to get y squared plus 1/9 equals to 1 minus 2y plus y squared. The y squareds get canceled out. If we take the 2y to the other side, and the 1/9 to the other side, we get 2y is equal to 8/9, which means that y is equal to 4/9. So now we can replace this y with 4/9. So then that is actually quite interesting, because we have 1/3 4/9. Well, here's the thing, 1/3 can be written as 3/9. So we have a right angle triangles with legs in ratio of 3 and 4. So this is reminiscent of our typical 3, 4, 5 triangle, which means that the ratios have to be the same. So this length C prime D would be 3/9, DI would be 4/9, and then C prime I would be 5/9. And that makes sense, because we know that C prime I is equal to CI. And we know that CI plus DI has to equal to 1. So since C prime I is equal to 5/9, CI has to also be equal to 5/9, and 5/9 plus 4/9 is equal to 1. So this verifies that this length 5/9 is right. We also know that this triangle EAC is similar to triangle CDI. And we also set up a ratio, a proportion between the sides. So now we can actually solve for the x in this expression as being the value of 1/3 times 2/3 by y. And since y was 4/9, we can just substitute that right in here. From here, we can cancel through, because 1/3 times the 1/3 in the 3 in the denominator would give us 1/9. Similarly, there's a 1/9 down here. So we get that x is really 2/4, or 1/2. So we can replace this x in our diagram by 1/2. So we have the legs of triangle AEC prime to be 1/2 and 2/3. Well, thinking of them with a common denominator, 1/2 is 3/6, and 2/3 is 4/6. So once again, since this is similar to a 3, 4, 5 triangles, we know that the ratios are also going to be 3, 4, 5. So we have 3, 4, which means the hypotenuse, C prime E, would have to have the ratio of 5. So since it's everything, like every other side is a 3, 4, 5 divided by 6, we would have length C prime E to be 5/6. So since it's asking for the perimeter of triangle AEC prime, we can add up these lengths for each side. We can add up the length 3/6 for leg EA, add the length 4/6 for side AC prime, and add the length 5/6 for length C prime E. And adding these three sides would give us the perimeter of the triangle. In this case, it would give us 12/6 or 2. So just like that, we have our answer choice A, to be the perimeter of triangle AEC prime. Now this problem was not too difficult. We just applied our simple geometry practices and just did a little bit of algebra to solve for those lengths. But this problem was not too unique, not too crazy. This is honestly a pretty standard AMC 10 level geometry problem, and you can probably find out many other problems like this that have shown up on AMC 10 exams for the past couple of years. And it just goes to show that you don't really need too much fancy stuff to take on these kinds of problems. You just need a solid understanding on concepts like area, similarity, and Pythagorean theorem. And you can even take out a number 21 on the most recent AMC 10B exams. So I hope you understand this video, and I hope it shows you that even the hardest problems can be solved just using a strong understanding of simple methods.